Okay, so I wanted to share this file system I've been working on for a while now with everybody. We could go on for days maybe about what's in here because it's fun and interesting. But we're just going to quickly cover the problem it's trying to solve and sort of the most important piece we solve and how we actually do it. We're going to get down into disk structure and stuff, so put on your thinking too because it's going to be a good one. So the space we're in are these customers who want a POSIX interface to their very long-term stable archives. So the idea is you'll have a POSIX namespace that is your archive for all of time. This is HSM, if that's your term you're familiar with. What makes this interesting? So, I mean, you know, as a kernel file system developer, you have this model of a file system in your head. And this gets a little bit weird, primarily for two reasons. One is just the file counts are very large. So anything where the operation you're trying to perform, where you just do a namespace walk, it just doesn't happen anymore. And at the bottom, we have things in the workflow that are typical searches, right? The basic software premise here, the promise you're making is that you write something to this file system, and some software agent somewhere else finds the new file and copies it off to an archive tier. And there's a bunch of policy knobs and all that stuff, but that's the basic idea. And so you can imagine if you have 10 billion files and one of them changed, finding it and getting it off to an archive tier stops being feasible. So that's one thing. And then we have a bunch of other kinds of search operations you do. A good one is the bottom one. Say you're archiving to tape because that's still a thing people do, and the tape gets hit by Hurricane Sandy. You have to find all the files that were on that tape, and so you can't just walk all of the files and see what tape they're on. That doesn't work. The other thing that makes this a kind of a weird environment from what we're used to is that there aren't file contents anymore. This POSIX file system becomes the authoritative database for the namespace and for the location of files off on the archive tiers. And all the files, once they're, the actual file contents, once they're on the archive tiers, they're truncated out. They call it offline, but they disappear. So you end up with a POSIX file system that's enormous and is only metadata. And that's very weird for all of us when we have this assumption about the ratio of metadata to data. I think that's all that's super interesting here. But so that's the problem we're trying to solve. Really big namespaces and all these operations that become impossible once you get these enormous file counts. It's a very classic system architecture, right? This is not super fancy stuff. We have a bunch of symmetric nodes and a bunch of shared storage. Software agents running on all the nodes, and those are working with archive tiers. Tape robots, on-prem object stores, stuff over the internet, though less so because our customers can't put it on the internet or they wouldn't be talking to us. And so scoutfs is what we're going to talk about. The POSIX file system at the bottom that gives you full POSIX across all these nodes while solving those problems we saw, right? There are two software interfaces that all those software agents use that make this possible. We can do the offline extents first because they're not that fancy really. In file systems, just like you'll have unwritten extent flags and extents, we have offline extents. And all that means is if you try to read them, you'll block. And while you're blocked, the software agents see that as a sign that we should go get the file off the archive tier and write it in so you can actually read it from the file system. And then some magic ioctls that truncate but leave behind offline extents instead of just freeing them, or write and then clear the offline flag from the extent. And this looks a lot like dmappy but isn't garbage. That's the difference. No, there's actually like version numbers and stuff, so you can't race with real writes. It's magic. But yes, it's still kind of frustrating. But the big one is that we provide an index of inodes. And we can index just about anything we want. Currently, we have the files sorted by their most recent modification. In reality, that's an index from the transaction number that committed a change to the inode back to the inode. But we have, in fact, in the past, and got rid of it, index files by size, by mtime, by whatever. We're going to add an interface so you can index files by user side xadders because a bunch of people want to do that. But the idea is that we maintain these indexes in the same atomic key value store that the rest of the file system metadata is stored in. So if you change the field of an inode that's indexed, we also update this main index at the same time in an atomic transaction. And then there's a software interface that the user space archiving agents can watch and walk these indexes. And so if you are an agent trying to find the most recently changed files, you just watch the end of the index, and files appear, and you know exactly where they are inside this 10 billion file namespace. So the indexes is the most important part, and that's what we're going to talk about for the rest of the talk. And understand it, it's going to be LSM again, because of course it is. This is just a basic overview of LSM, and understanding this will help you understand how it is that we can keep these, because those indexes are global, right? It's the entire namespace. So in theory, they could be a really bad point of contention, but LSM lets us get around that, and we're going to find out how. Maybe everybody knows how LSM works, maybe not. LSM is just an organization of a bunch of log fragments, right? I tried to be cute with little examples of the ranges of keys that can be found inside any LSM. I call them segments, some of the literature calls them files, whatever. These are all fixed size. So you make a tree shape out of these segments, and what's important to realize is that the way LSM changes over time, new data comes in at the top at level 0. And those new segments are totally unstructured. They are, it turns out in our world, each segment is a transaction that has a bunch of related changes and a node writes it. But the next one over can have, there's no limit to the number of, or any of the relationship of the keys in there. They can be totally arbitrary. So level 0 is more like a classic log structure thing where it's just a number of transactions ordered by time. And those just arrive as new data arrives. The rest of the LSM structures is more orderly. I don't want to call it strictly structured because you get a lot of flexibility out of how flexible this structure is. It's not strictly balanced like a B tree. It's much more sloppy, actually. So in the rest of the levels, a given key only exists in one segment at a given level, and they're all sorted. So to read a key, for example, if we wanted to read B, we would only read one level 0 segment and that one level 1 segment. We use the most recent one we find, it's the level 0 one. If we wanted to read A, we'd have to read all those level 0 segments, that level 2 segment, and use the most recent one. But you can see that whenever we're looking for a key, we only use one segment at a given level. That's how you get an index out of this thing. You limit the amount of stuff you have to read. You need a structure that describes the layout of the segments, but we'll get to that. And then we won't really need to talk about compaction, but compaction is how you maintain the tree shape here. As all these level 0 segments arrive, eventually that's just a big long list of segments, and it can't go on forever, or you have a linear search to do anything. So compaction starts to merge those items back down into the main structure, and that's how it grows over time. But for what we're going to talk about, what's important is new stuff comes up at the top and then gets pushed down. I hope that helps. So this is how scoutfs lets us maintain this global index while we're doing these transactions. This is where it starts to get interesting. In that last slide, we saw that LSM structure. That has to exist somewhere. You have to have a structure that describes where the segments land in the LSM thing. In the literature, it's the manifest. We store the manifest in a B tree on disk. But the way we maintain the B tree gives us a lot of concurrency. It's in a pre-allocated ring. Writes are always just in this advancing tail pointer. And so at any given moment, a bunch of nodes can be reading old versions of the tree, and somebody can be writing a new version. And this lets, well, it just gives us a lot of concurrency. It lets any node, if it knows it's safe to, and there are locking protocols that tell it this, it can walk any old weird version of the B tree and be given references to weird old versions of LSM trees, but the data's still valid because they had a logical lock that protected the thing they were looking for, even though the B tree and the segments were shifting under them. They have logical consistency. And this gets rid of the physical indexing point of contention that would be real bad for this database otherwise. I think that's all we need to know here. But the amount of concurrency here is what's important. So this is where it all goes. This is what makes this system interesting. This is what lets a bunch of nodes be updating inodes in this big POSIX data store and updating a global index without stomping on each other. Because what they do, each node represented at the top here has a transaction open. And let's say in this example, they each have an exclusive lock on these inodes, A, G, and R, totally arbitrary, whatever. But then they have shared write locks on the index stuff, all the things they're going to change in the index. So this first node read A and saw whatever we're indexing was 1. I don't know if it's M time, who cares? And so it gets a shared lock on the old version and the new version, and that lets it emit these items into the level 0 segments in LSM. So as long as all these nodes are working on stuff that doesn't intersect, and that's very often the case because this namespace is huge, so the likelihood that you'll step on each other is surprisingly small. As long as you have exclusive access to these things, you can get shared access to the whole index. So all these nodes are emitting these index items at the same time. There's no contention on locking the index because all they're doing is gathering up these dirty items and spitting them out in LSM. And the way they update the manifest is with some RPCs and stuff, but the core thing here is that they don't have to all lock some global B-tree index to spit out these index items. This bottom one is to demonstrate what the rest of the LSM tree looks like while they're doing this. So the old level 0 stuff was the state before anybody did their work here. And just by the way we sorted it, all the index items are first. So there's these index items that say, if you're looking for whatever M time 1, you're going to find A, 10 is G. But up in the level 0 segments, that's all changed because the new writes have landed. And so if this were now the persistent state, and someone were to try and stat an inode, they would read the level 0 one, but they'd also read that old level 1 segment, but they'd use the level 0. The power of LSM is that you can write these little log fragments anywhere, and readers don't go to one place. Readers combine a bunch of log fragments. And so writers can write wherever they want. That's where you get the parallelism out of it. But that is it. That's all I had. So if anybody has questions, I hope we have questions, because questions are far more interesting than just spewing this thing out. So that's what we're working on. Anyone want to talk about disk structures? Anything? Yeah, they're pretty pictures, huh? Yeah.
So can you give us some sense of what's the workload that causes the metadata updates? Like what are the characteristics? Like it's kind of all kinds of whatever crazy HPC stuff or what?
Well, no, so these are archiving appliances, so they're generally this dedicated standalone thing. And so at the very bottom, that's the kind of workloads that happen. But say, for example, we're on the other side of a big HPC cluster and they're doing these big checkpoint drops, and so they're dumping big old files in here. What the archive agents will do is first a big old read to find all the files that changed. They'll dump all those files off onto the archive tier. So far, scoutfs has only seen reads, right? So a bunch of parallel work. But then they want to update the database of where files are in the archive tier. For us, that's XAddrs. So all these archive agents will set these XAddrs on all the inodes they just archived, and that's it. So for this archival workflow, where new data is coming in, we're archiving it. It's a bunch of parallel reads to get all the stuff and put it on the tiers, and then a bunch of little metadata updates. But with a lot of little files, all of a sudden you have, say you have a bunch of nodes all doing a big ingest. All of these nodes are working on these groups of files independently, and they're all doing these set XAddrs, which are all updating this global index. And so if we couldn't have concurrent updates on nodes to the index, that simple thing, that final update the record of all the XAddrs, would be globally serialized, right? We have to be able to concurrently update all these indices wherever they are in the namespace. That's one load. There's a lot of other stuff, but that's the big one. There's archive management loads where you need to re-archive stuff or you do media refreshes, but a lot of it comes down to a bunch of metadata updates on these files, right?
Okay. So most of the workload comes from application pattern or from utility cleaning
stuff.
Up the system? Or
yeah, so these...
those seem like they could be different.
Yeah, this is not a general purpose thing. People don't really run their end of line software on this, so that second point, this is often an explicit interaction with an archive system. So you rsync crap over, you do some little online portal thing, and it does management behind. If it's an HPC, they often have these fancy connectors that know how to talk to Lustre efficiently and dump it into this thing well. But they want it to be POSIX because they're used to POSIX, right? That's all their management stuff.
So I was wondering, how do you clean up the mess whenever you, and someone else described this similarly, when you add to an LSM tree, you add stuff to the top tier, and then you have to clean it up every once in a while. So when you go to clean it up, you have to start modifying the levels below. People can still read because the top level is what they go after first and they get the most current information. But at some point, you have to lock the lower levels as you work on them for people who are going after the old information.
Right. Yes, you do. So compaction is the operation that moves segments around the tree. A given segment is immutable. Once it's written, it'll never be written again. In the compaction process, let's take an example here. Yeah, if we were to compact away that first segment in the level 0 list there, the operation is to take a segment, read all the segments lower that intersect with it, you read them all in, you sort them all out into new segments, write them all out. In this case, it would just be level 0 and level 1.
But that would be a huge atomic blocking thing.
It's a lot of extra bandwidth, and that's actually a really interesting aspect of the system. But let's finish the thought on how we actually lock that update. So the new segments, the output of that compaction operation, are written to free space. And so you have to have this atomic update of the manifest that describes what is where in the segment. That's what the H and I write here would be in this diagram. So that old state pre-compaction can still be being worked on, referenced, read by any old nodes, because none of it's rewritten by the compaction. We write a new version of everything.
Okay.
And that's all done with RPCs and stuff.
Then how do you clean up the mess of all those old nodes that you are no longer referencing in the new B tree?
They're marked free in the newest version of the blocks that are written in H and I is allocators that say those old segments are now free, the little B tree references to the segments that describe them in the place and all that stuff.
And if somebody was reading those while it was being compacted, they would be referring to things that just got freed up.
Yep, and that's fine. We have a bunch of metadata that tells a reader if they've hit stale stuff. That's one of the really interesting parts of this.
Okay.
They read it in, they say, oh, that's corrupt garbage, try again. They get a new B tree root and they reread the thing. But you did bring up an interesting point. I don't really have a slide on it. LSM in general introduces an immense amount of compaction, read, modify, write overhead, but it trades off IOPS for bandwidth.
Concurrency.
That's one of its fundamental trade-offs.
Okay.
So even in the worst case, this thing clobbers all the 4K B-tree systems because they get IOP bound doing all these fiddly little bits. And this thing is dropping down these 1 meg streaming writes.
Gotcha. Good stuff, though. Thanks.
I think this one's my favorite. Anyone else? I have no idea where I am in the window.
Yeah, you're we still have 2 minutes.
Woo!
Otherwise, you're catching up.
Joseph's got a thing. Yeah. Throw the good rocks.
So you said that, can you go to the next slide? Or I guess the previous slide. There we go. All right. So you want A, right?
Yeah.
And so you need to read level 0 and level 2. Why do you need to read level 2?
Why do we need what?
Why do you need to read level 2 if it's in level 0?
Oh, if you read them sequentially, you'd find it. But we read them all concurrently and then walk them all concurrently. Because when you're choosing to read segments, you're just looking at the manifest, and all it tells you is the bounds of the keys in every segment.
It doesn't tell you where.
It doesn't tell you specifically,
Okay.
and that's a read amplification problem.
Right.
But we read them all concurrently, and we never actually just import one key. All the locking and stuff is ranges, and so what we actually do anytime we have to read is read us. You can imagine sometimes these look like stacks. You have a segment from every level, and we iterate over the range of keys we're allowed to have cached based on the locking, and we ingest all of them, including the one we read. So we like to get as much surrounding context as we can.
Gotcha. And then you just compare transaction ID or whatever and grab the newest one.
Yeah.
So then I lost it. So I had a question. So you said that if you're reading stale data that you free off or whatever, the reader will come back and say, and be told that, by the way, this might be garbage.
Yeah.
How does that mechanism work?
What does it what?
How does that mechanism work? How does it know?
So sequence numbers and little identity things and all these metadata blocks stored in the source of the reference. So if you try to read a B-tree block and you hit sequence 17 instead of 16 or whatever, it says, oh my God, it's all changed, start over. And what starting over means is you ask the server, there's a negotiated server thing, for a new B-tree root, and you just start all over. You read the manifest, you read the segments and everything.
Oh, I see. So if the block got freed and reused, and while you were reading it, you would read it and see that there was a new sequence number and retry.
Yeah, and you back way the heck off.
Okay. So you're not worried about like in-play, like different updates? Well, I guess not. Yeah, okay, cool. I'm good.
Checksums, they're the thing.
Yeah.
Okay. Thanks, everyone.